Okay, so as Ronnie said, I'm going to basically go through some research I did as part of an MSc I just completed. Hopefully this presentation will make you dizzy because it jumps around a bit. So I just recently finished the MSc in Trinity College. It was an MSc in bioengineering. I did it part-time while working full-time in the hospital. So what I'm going to speak about is a thing called unilateral spatial neglect. And this, I'm going to go through what it is, how it occurs, how it affects the patient, and also how often does this happen. So just to give you a brief introduction about what spatial neglect is. There is a definition that's used. It's an impaired or lost ability to respond to stimuli presented in the contralesional hemispace. So contralesional is the opposite side of the lesion where the brain is, and hemispace is just your visual field. The important thing to take from this is that it's not a visual defect, it's an attentional disorder. So visually we can prove through EEG signals that they see objects on the contralesional side. They just don't pay attention to them. The link to the brain here is that the attention is lateralized to the right hemisphere. So as I'll discuss now, we have about 3 to 5 million strokes every year, and about 60% of those strokes display symptoms of spatial neglect. Out of that 60% that display symptoms, about 90% of them all occur from right hemisphere damage. So how does it occur? Fiona, who's speaking after me, is going to talk a bit more about stroke. I won't go into it, but basically two types of stroke, ischemic and hemorrhagic. The ischemic is where the artery becomes blocked with plaque and there's no blood flow and the brain is depleted of oxygen. Hemorrhagic is where the artery wall thins and you get a bleed in the brain. So how does it affect the patient? Well, it can be quite severe. It can also rectify itself quite quickly. Typically within about a year, about 60 to 80% of patients fully recover from this. But some of them have long-term illnesses that go on for most of their life. These are some of the examples. You'll see here on the right-hand side, the person shaven. It's a bit of an exaggerated example, but it's called personal neglect. And they basically ignore the left-hand side of their body. So they think that's fine. They look in the mirror, they shave, and they think they're completely 100% done with what they need to do. The same with their dinner. They'll ignore the left-hand side of their dinner. The interesting thing with that is, if you then turn around the plate to the opposite side, they won't eat the right-hand side. They realise that the image is turned. It's not a visual thing. The left-hand side is just an example of some of the tests that they do. You see the left of the left picture shows the ideal picture, and then it shows what the clinician would have asked the patient to copy. And they will often just draw the 1 to 7. Sometimes on the right side of the clock, they'll include the whole 1 to 12. But they think that's fine. If you ask them to review it, they think this is normal. The same with the house, they leave out the left-hand side of the house, the left-hand side of the flower. So, I've discussed how often it occurs. So these are the current methods that are in place. On the left-hand side, you see there's a method that's most commonly used, which is star cancellation, where the clinician asks the patient to cancel out all the small stars across the page, and the patient sits at the midline of the page. You'll generally find with neglect patients, they don't cancel the left-hand side. Similar with line bisection, they'll bisect to the right-hand side of the line because they don't pay attention to the left. It's not that they don't see it, their brain doesn't process it at a higher level. And I've already discussed the figure copying. There's one problem with these diagnostic methods though. They're all very subjective. How do you track the severity of the syndrome if you're looking at how somebody is copying a drawing? It's very hard to do. So, working as part of the neural engineering group in Trinity, our hypothesis was basically to use what's called a random dot motion direction discrimination task, which was developed back in '92. But I think rather than going through the whole thing, the main thing to realise here is that it was to be used objectively to try and detect the presence and diagnose the severity of the neglect. And this is really important to try and track somebody's rehabilitation as they go through any treatment they're having. So here, some of the questions on the right were just research questions that were proposed. Can this task evoke a decision signal known as the CPP? Anybody that might be aware of or involved in neuroengineering, you might be aware of a P300 signal, which is a decision-based event-related potential. Well, this CPP signal was only developed in 2012, or discovered in 2012, and it's basically the competitor to the P300. So we wanted to find out, could this decision signal be evoked through this task, and could it show changes in how the patient's evidence accumulation changes? So I'll explain it a bit further as we go on. This is the task, the RDM task. You see on the left-hand side, this is what the patient sees. So they're in a dark room. All they can see is a screen with 4 patches of moving dots. All the dots are moving incoherently. They have to stare at a central point at all times. That makes sure that we capture the whole visual field. The stimulus then occurs, which is a certain range of coherent dots moving either upwards or downwards. As soon as they see it, they click the mouse. And I'll go through some of the difficulties we had about that later on. So the measurements that we took as part of the research was the typical pen and paper results, which were the current gold standard methods that clinicians use. And then we looked at the behavioural data using this RDM task. So we looked at the accuracy of detection, we looked at reaction time to the stimuli and to the peers, and then we also took EEG data. So we looked for this signal known as the CPP, and we also looked at another signal known as alpha band activity, which is a certain frequency range of signals that occur in the brain, but it's been proven to be very closely related to attention. So, just quickly go through some of the main results that I got from the research. If we look at the pen and paper, which are nothing new, we'll see that the patient which is in the blue, for the left and the right means that hemispace. So the left-hand hemispace is where the target occurred, or the right, and similarly so with the lower and the upper. You'll see that the patient scored significantly below what the control group scored on all ranges or all visual fields. But you'll see the difference between the left and the right for the patient in the blue, here and here. Looking at a line bisection, it's not just about bisecting the line, they also omit lines that are on the left-hand side of the page, which is something to do with object-based neglect. Looking at some of the behavioural results we got from using the RDM task, we could see similar results in how accurate they were at capturing these stimuli. So you can see that on the left-hand side, the patient scored significantly low between the left accuracy and the right accuracy, showing that they didn't detect the left targets as easy as they did detect the right. The control didn't have much of a difference between left and right. Looking at reaction times, you'll see that the patient was significantly slower at detecting the targets, but not much of a difference between the left and the right. There's a reason for that, because our data was quite limited in how much we could use from the stroke patients because of their conditions, and I'm going to talk about that in a minute. We also looked at some EEG signals, and this main one is what I'm going to tell you about here is what's called the CPP, which is an event-related signal, or event-related potential. And it's supposed to occur about approximately 250 to 300 milliseconds after the stimuli occurs. So the stimuli occurs at time 0, and then we see a slight dip, and then an increase, which is your event-related potential. Ideally, what we want to see is something similar to this, where you have, for the blue is left-hand targets, where you have left-hand targets, there's a lead in, this is for a healthy patient by the way, there's a lead in the evidence accumulation that occurs. So we were hoping to see that we would see a lag in the left-hand targets because of their inability to detect them as quick. What we actually found was that it was really hard for the patient to detect the target in the first place, so our data was very low. And again, I'm just going to touch on that in a few slides later. This is some alpha band activity that we looked at as well, which is basically looking at the power of the signal on the brain in an alpha frequency. So I won't go into too much detail because the results weren't too significant, but you'll see here this dark blue area here for right hemifield targets occurred in the left hemispace of left hemifield of the brain, which is hemisphere of the brain, which is typical of what happens. The left hemisphere controls the right, and the right hemisphere controls the left. So these results, I believe, are just the tip of the iceberg. We unfortunately couldn't, the amount of patients we got because of the limitations we had with ethics and with patient conditions meant that our data wasn't significant enough to draw the correct conclusions. But we did prove that this RDM task does evoke this signal, which has already been proven to be similar to the P300. So we know it works, but in talking to researchers in Australia that are leading this area of research, they typically take only 2 patients out of every 20. So they test 20 patients and they can only get 2. And in a top master's, unfortunately, I don't have the capacity to get that many patients, but that's the level of where you're going to try and test these patients at the minute. So we need to look at some of the challenges and limitations that we have within the project. So as I said, the ethics was a huge part of it because of the neural engineering side of the project and the fact that some people see it as kind of encroaching on someone's personal space, reading their brain signals, trying to figure out what they think. Ethics look at that very closely. Also the fact that there's so many subtypes of neglect. It's really hard to figure out. There's sensory neglect, there's motor neglect, there's what's known as representational neglect, which is a really interesting one, I think, in that if you ask a patient who has neglect to look in the centre of the room, they won't describe anyone on the left-hand side. Just if they were to imagine it, let's say they're not here, if they were to imagine the left-hand side, they won't describe anyone on the left. If you then ask them to go to the other side of the room and look back, they'll then ignore the left and they'll ignore their new left, which was their right, even though originally they could see it just in their imagination. So it's really interesting to see how the brain works on a higher level. Task compliance was probably our biggest problem. Most of the patients found it hard to even understand the instructions. The task was quite basic, it was just simply a mouse. Or so I thought, it was simply a mouse. But most of the patients I tested had an age profile of 60 to 80 and they didn't even know what a mouse was. So I simply said left click the mouse and they looked at me and said, I don't know what that is. So they didn't know how to hold the mouse, they didn't know what the computer screen was, and even then the environment and so on. Left a lot of things to be improved in the future. The attention levels and fatigue. I had patients who fell asleep during the task. I had patients who couldn't attend to what was going on the screen. They just said they couldn't see anything, even though visually they had no visual defects. And obviously hemiplegia then, because you have an EEG cap on you, hemiplegia is basically where you have paralysis on one side of the body. And with the EEG cap on, they couldn't hold the body up straight all the time, which meant that their body was sitting to one side and they had a chin rest, so their head would hit off the chin rest and distort the signal. So all those type of things ended up being real challenges that we didn't predict happening. The limitations, I suppose the main limitation is in typically of these EEG studies, you have eye tracking. And the eye tracking makes sure that you focus on that midpoint that I showed you earlier on with the RDM task. We couldn't have eye tracking because most neglect patients have a biased gaze direction to the right because they're ignoring the left. So that was a problem which led to the movement artifact. And it also meant that we couldn't see where they were paying attention to. We couldn't see if they were focusing completely on the right, and therefore their visual field wasn't even on the left. They reminded of what their attention was. Also the signal quality, as I said, the low number of usable trials. We had a lot of EEG trials, which are perfect signal quality, but they just flatlined. It's just the brain isn't creating the signal. Even though we could see visually it would evoke the potential, it just didn't process it further on. So there were some of the big issues. However, I suppose the main 2 areas of future work would be to improve the signal acquisition methods. Stuff like dry electrodes and portable EEG and wireless EEG is the way forward. It took a long time to cap up the patient. It takes a long time to clean the patient's hair afterwards and so on. So it's not a test that's ideal right now to put in practice, but the background theory is there for it. Another thing is this thing called VLSM, which is a voxel-based lesion symptom mapping, which is where you basically map the neural behaviour to different regions in the brain in an attempt to try and isolate what regions of the brain are responsible for the different parts of the neural behaviour. The last thing I just want to say is the future applications. So it's known and it's widely reported in the literature that neglect cannot be assessed properly at the bedside because of the fact that it's not in a busy environment, it's not in a real environment, it's very hard to simulate. So integration into 3D virtual reality environment is the way forward, and using EEG to guide your way through the likes of a walkway with obstacles and so on. Where I see this being useful is in the rehabilitation. This is a 3D video game that was produced by my supervisor, actually, Dr. Evan Blogger in Trinity College back in 2005. And this is my last slide, what this does is, this basically tracks your attention between the left and right side of the tightrope. So this character here has to walk along the tightrope, and they have to, if the character is falling to the left, you have to look at the right hand side. So the application of this could be that it just creates a consciousness within the patient that if the character is falling to the right, the patient has to start looking to the left. And it uses an EEG-based system here with these two checkerboards flickering at different frequencies to look at where they're looking. And I think that could be a great way forward once we get by the initial challenges. And that's it. Thank you very much.